At this point, we've done the majority of the work it takes to prove that Quicksort is correct. We've proved most of the code is correct. Most of the code is that loop invariant, that loop, the partition loop. Now we just have to tidy things up by doing a proof by induction on the parts that sort of wrap around the correct partition procedure. So let me remind you of a proof by induction in general. We have some property P that we want to prove is correct. We're going to have a base case, so some statement regarding what happens when we have just the smallest unit of our input. We're going to have an inductive hypothesis that says, let's assume that P of n is true, and then an inductive step where we say that if P of n is true, then because of something, we know that P of n plus 1 is true. For Quicksort, we're going to do this a little bit differently. So instead of going from n to n plus 1, we're going to do something more like going from n minus 1 to n. So just like shifting these two things backwards. It's still the same style of proof by induction, but just a little different. Instead of n minus 1, we're going to just say for any k that's less than n. And why we're doing it with something less than n will make sense as we work through this proof. Okay, so we'll say if P of k, where k is less than n, is correct, then P is also correct. So we're going to say, let's assume in our inductive hypothesis that P of k is true. Then in our inductive step, we're going to say P of k is correct, and so is P of n because of whatever our reasoning is. I know this is kind of vague. It'll help when I actually attach this to some code here. But again, I'm going to give you this as sort of our cheat sheet for a proof by induction. We're going to say that P of n holds for all of n. So P of n, the property we want to hold for everything. We start by proving the base case. So P of 1 holds because something about the code. This is where you actually reason about what the code does. So if we have a single element in Quicksort, our Quicksort implementation just returns that single element because it's already in correct sorted order. So that's the base case. Then we're going to assume something about P of k where k is less than n. So we're going to assume that P of k is correct. Then we say that P of n holds because P of k and then something else about the code, the non base case part of our code. So in fact this will be sort of the partition part of our code, which we've already proven is correct. Partition. So this is our general framework. Thus by induction P of n holds for all. So why does that work? Well, if we know that this step works, and we assume that P of k is hold. Well, why can we assume that P of k holds? Well, because P of 1 we proved, and this step here is the same as the step over there. It's always the same inductive step. So we can just follow that inductive step all the way up to P of k, and then if we prove something about this, then we've proved something for P of n. So that's our proof by induction. So let's do this for Quicksort. P of n is our Quicksort implementation, and let's say it's correct on all arrays of length n. So that's the property we want to prove. P of 1 is an array of one element, and any such array is always correctly sorted. So that's our base case. Trivially true. We don't even have to dig into the code, really, just to say that it automatically returns when you have a single element. Our inductive hypothesis, we're just going to assume that P of k is correct for all k less than n. So P of n holds because we have Quicksort called recursively on its two partitions, so the left partition and the right partition. Well, let's let KL and KR, so K left and K right, be the links of the left and right subarrays. We know that K left and K right are strictly less than n. So how do we know that? Well, if you take all n elements and you subtract one out, then no matter how you split up those elements, even if all are to the right or all to the left, you're going to end up with some number of elements that's less than n because we've taken one out of it. By our inductive hypothesis, we know that the recursive calls sorting this part and this part are correct. That was our inductive hypothesis, that P of k holds for any k less than n, and we just said that the recursive calls operate on items less than n. Well, the partition loop invariant guarantees that the pivot is in the correct spot. So we know from our inductive hypothesis that the left side is correctly sorted, the right side is correctly sorted, and that the pivot element is in its correct spot based on our loop invariant proof. Now we can say that our Quicksort implementation is correct. So we have our base case, our inductive hypothesis, and our inductive step where we reference what our code is actually doing. And like I said, we're just going to refer to all the work we did in that proof by loop invariant. Alright, so we've proved that partition works correctly, and we've proved that Quicksort works correctly.